All right, so we were talking about the asthenosphere. The asthenosphere, just to make sure we got that straight again, because I keep pronouncing it. But the asthenosphere is the bottom part of the upper mantle. Okay, sometimes I keep saying it's the bottom part of the mantle, but keep in mind there's the lower mantle down here. It is solid. Even though it's hotter, as you go down through the Earth's surface, it gets hotter and hotter, but you also are getting more and more pressure pushing down those rocks. So keep in mind, we think of melting having all to do with temperature, but technically it has to do with pressure as well. But the only pressure we have on the surface up here, we only have the pressure of air pressure, and it's pretty much constant everywhere. There would be a little bit less air pressure if you're on top of a mountain up here. There'd be a little less air pressure, but basically air pressure is pretty constant and the same everywhere. But now as we're going down into the Earth, we're talking about extremely high pressures as well as extremely high temperatures, and so things kind of act a little differently down there. Okay, and so we said you had the asthenosphere, which is plastic, which means that it can flow, it can move. We said it even has convection currents that flow, although it takes 100 million years, we think, probably for it to go all the way around. So we may be talking about a flow of inches or feet per year. Okay, very, very slow, steady flow. Okay, and then the upper part of the upper mantle, right there, this upper layer up here, is actually considered to be part of the lithosphere. Okay, so we have the asthenosphere, which is the lower part of the upper mantle. The top part of the upper mantle and the crust are considered together as the lithosphere. All right, and so this top part of the upper mantle, why is it considered part of the mantle then if it's connected with the crust to make the lithosphere? Well, basically, remember the Moho discontinuity is where the earthquake waves speed up. So right along this line, there's more dense rock, and because the dense rock was originally labeled part of the mantle. Okay, but when we talk about how it moves, and we talk about how this crust part up here moves that we talked about here, it's not just the crust, it's also part of the more dense rock at the bottom, which is part of what we call the mantle. So to talk about that, we talk about the lithosphere, and that's just the crust plus some of that upper mantle. Okay, all right, but just for the record, all of that moves. Okay, and so really, functionally, as how it works, it might be better to draw a boundary between the mantle, the asthenosphere, and the lithosphere, because all this other top part tends to kind of move as a group, as a united part. All right. So this lithosphere part of the mantle and the crust tends to act as a group, and like we said, it moves. As these convection currents move, they move these top parts, and it's not all connected. We think it breaks into pieces kind of floating on top here, and those pieces are called the different plates, okay, or tectonic plates. We'll talk about that in the next chapter, but there's the different plates of the crust and upper mantle that move around. These pieces move around very slowly, once again, but they do move around. Okay, and they're floating on the asthenosphere. All right. Now, if we want to talk about the actual crust, okay, some things we should say about the crust. The crust is the very top of the lithosphere, very top layer. It's divided from the mantle by this Moho discontinuity, where the earthquake waves speed up because it's denser, heavier rock. Okay, we have two types of it. We have oceanic crust and we have continental crust. All right. All right. Now they're not going to look exactly the same. Let's look at a picture real quick. Let me get rid of all that stuff right there. All right. Basically, the continental crust. Let's do the oceanic first. All right. The oceanic crust, first of all, notice is not very thick. Okay, oceanic crust is about 10 kilometers, which is about 5 miles deep. Now, some parts of the ocean there may be trenches, so that goes down into that a little bit. And so it's not going to be the same everywhere, but approximately about 5 miles deep. Now, the continental crust, on the other hand, is anywhere from 20 to 60 kilometers, and that would be about 10 to 30 miles, give or take a little bit. Okay, so depending if you're up on the plains in a very flat area, or if you're in a very mountainous region, this has been kind of exaggerated. The continent wouldn't go up be that steep, okay, in that small amount of time. But basically, the thickness of the crust is going to vary depending on the mountain ranges and things like that. Okay, generally speaking, the oceanic crust. Okay, the oceanic crust is very dense rock, very heavy. That's why it sinks and sits lower in the water, as it were, whereas the continental crust is less dense and it floats up. So it's less dense. The oceanic crust is made from basalts or basaltic rock, okay, which is primarily volcanic and it is very dense. The continents are made from most common is granite, so they're called granitic. It just means they're made out of granite and they're less dense, less heavy rock. Okay. Now, the reason, even though the ocean crust is thinner, it is heavy, okay? And because of that density, it will sit lower in the water, kind of like we have a ship here. If we have a ship here empty and it's sitting in the water at a certain depth, as you put more and more stuff in it, now it pushes it down and it sits lower in the water. Well, that's kind of what the oceanic crust does, is it weighs so much that it sits lower underwater, basically. Even though it's not as thick as this, it is going to sit lower in the water, and the continent is going to sit higher up in the water because it's less dense. And so it's very important. That's the main reason. It's the importance of the basaltic and the granitic is because that affects how they sit down. The ocean crust stays low in the water, underwater, and the continental crust is lower, higher and floating. This idea of how they float in here, kind of like a boat floating here. Here you have gravity pushing down and the buoyant force of the water pushing up on it, and they have to get in balance. Here we have the same thing happening. And this is called isostasy. Isostasy, and basically isostasy means they want to equalize. You've got gravity, the weight of the continent pushing down, but since the asthenosphere acts kind of like a fluid, it pushes up on it, and these two things have to kind of equalize it. All right, and once again, that is why, and so it's just the equalizing of the weight, which is gravity, caused by gravity, pushing down, and the buoyancy of the asthenosphere pushing up, and that equalizes it and makes it, and that results in, since the continent crust has less density, it sits higher up in the water, if you will, and the oceanic crust is lower because it's more dense. Okay, and that's all that concept has to do with, really. Now, as you can imagine, if you have a fairly rigid crust up here and lithosphere floating on top of a fairly fluid, okay, that gives underneath, you can imagine that there's not always going to sit there silently. Okay, there's going to be pushing and pulling and stresses on the crust. Okay, and an important concept is elasticity. We don't think about rocks or rock layers as being elasticity. All right, elasticity. We don't think of rocks as being what we call elastic, but what elastic means, when we say that rocks are elastic, what we mean is that a material, once stretched or put pressure on, okay, once it's stretched, it will return to its original shape once that stress is removed. All right, so basically if something's elastic, it means if we pull on it, it will stretch, but then it will snap back. Think about the waistband of underwear or rubber band. Okay, you stretch it, it's very elastic, but it's elastic because it will snap back to its original shape eventually. If you continue to do that over and over, even your rubber band and your elastic underwear will begin to sag and stuff and not quite snap back to where its original place is. Same thing happens to your skin as you get older. It doesn't snap back and it gets stretched and you get wrinkles and all that kind of stuff. Same general principle that we're talking about here. So rocks, we don't think about rocks as being able to snap back, but actually most rocks are fairly elastic. They can, when there's some kind of stress on it, such as temperature, pressure, and so forth, it can go back to its regular place once that pressure is removed. But not all rocks. Some rocks are more elastic than others. Okay, and so how elastic a rock is going to have to do with several factors. It's going to depend, first of all, on the temperature. How hot is it? Okay, as the hotter it is, the more closer it is to melting, so it's more likely to be moldable, just like anything else that you bend. If it's hotter, it tends to be more flexible and stuff. If it's colder, it tends to be more brittle. Okay, it can, the pressure, the amount of pressure being put on it, and it can also depend on the composition of the rock. Some rocks are more amenable or willing to bend, others no, and so it doesn't take much and they just snap and are very brittle. All right, so in general we would say that brittle deformation just means changing their shape. So these different stresses that pull on this crust floating on the asthenosphere, it's going to be brittle. It's going to cause deformation or change in the shape. Okay, it's going to be brittle deformation generally if you're at low temperatures. Okay, we said basically cold things tend to break or snap easier, and so if the rocks, if we're talking about rock layers and they're at low temperatures, they're more likely to break. Okay, and so the brittle, they just snap in two when you push on them. Okay, the pressures at the Earth's surface, okay, are going to be more likely to cause brittle deformation because these don't have a lot of pressure on them, and therefore they're not melty and flowy like the asthenosphere, and so they tend to want to snap or break. All right. Now, when they break, they can form a couple of different structures. All right. Anytime you put pressure on them, then they can cause two sections to snap or separate. Okay, generally they tend to have kind of a slanted, whoops, sorry about that. I think you see sick there, but they have a slanted surface here. Okay, if you pull them apart, okay, tension forces pulling out, okay, then they're going to fall down. And when you have this slanted part, the miners used to see these inside the mines, and so they would say the one slanted like this, is slanted down, that's the one you could walk on. You can't walk on this one, okay, but you could hang things like lights and so forth off that. So this is called the footwall, okay, and over here would be called the hanging wall. All right. And so we use that terminology to name faults and so forth, okay? So on this one over here, you can see the fault plane right here. So this one here would be considered the footwall because you could walk on it. This one would be the one slanting kind of over your head, so that would be considered the hanging wall. Okay, it just has to do with that tilt. If it's tilt where you can walk on it, then that's the footwall. The other one is that. Now, these can be caused from two ways. They can be caused by being pushed together, or they can be caused by pulling apart, and we can talk about that later. Now, when these move, that is called a fault. So you've always heard of fault lines and so forth. Well, this is fault plane or fault line right here is where these two layers have moved. Okay, and when they move compared to each other, that is a fault. All right. Now, these are all when it's brittle, when it kind of snaps. Okay, but if it's fluid, okay, these are what we call brittle deformation. Plastic deformation occurs inside the earth more often, where you have higher temperatures and pressures. Okay, and the higher temperatures and pressures, when you push or pull on these, rather than snapping, they tend to just, say, for example, fold up. And so a lot of times you'll see on the side of the road, you'll see these folds like this, and that's more from plastic, and you know that that originally occurred probably somewhere deeper in the earth. It may be at the surface now, but it was probably not at the surface when those happened. Okay. Last thing we need to do is fill up a couple about the types of stresses that cause these faults and these kinds of deformation, and then we will be done with the chapter.